Good morning, Tahoka. Let me see if I have some volume. Yes, I do.
Good morning.
How's Tahoka? Are you good?
Good. How about you?
I'm
Yes,
doing well.
ma'am.
Okay, let's see about our other schools. Um, are we there yet, or Rawls?
Good morning.
Good morning. There's Rawls. Half a Rawls. Idalus? Are we connected? Michaela, is Emmanuel going to be there? Do you know?
I actually don't know.
Okay, that's okay.
He should be though, because he has a game today.
Well, I don't hear anything from Idalu yet. Okay, students, just a little information. I've gone back and forth on having just a test that would be 50 minutes, and then there's Idalu. Good morning. Y'all aren't going to talk to us? Okay. Back and forth, I've gone back and forth about having just a test that would be 50 minutes covering all of this with your graphing, polynomial graphing, your rational functions, where you have your vertical and horizontal asymptotes, and then your number line graphs that just are a easier method to see where your other types of graphs would be above the x-axis or below the x-axis. The ones shading on the number line, the inequalities, and then all of your logarithm things. And I just cannot think in my mind that I could give an adequate test for both parts in just one day. So I'm going to be typing up a revised schedule. Basically what it is I'm just going to push everything back a day, but I'll go ahead and type one up. So your test next week, it will be 2 parts, and facilitators, I need you listening also. 2 parts on the test next week. Wednesday will be, students, your graphing part, the polynomial, the functions, the rational functions, and your inequalities. Then, and all of that will be done. That'll be, I'm not sure that it's going to be 50-50, but it'll be close to 50-50. And you will do that part on Wednesday. Facilitators, you will collect that. And I haven't completely made up my mind on the homework. I think just the homework for those pages, and I'll let you know what pages, okay? So that between Wednesday and Friday, when you take the second part of the test, you can have your logarithm papers to go back over also. So I'll break it apart into the 2 parts. On Friday, then your test on the the logarithm parts where we started our exponential and logarithm equations and properties and all of that, okay? So I'll give you the exact, well, I can give you the section numbers even right now. On Wednesday, the test will be sections 3.1, 3.2, 3.3, and 3.4. And then on Friday, it will cover the rest of it, 3.5, 3.6, 3.7, and 3.8. So that's pretty much a midway break, and that way I can give, each problem won't have to be quite as many points because I can actually give more points breaking it in, more problems breaking it 2 days like that. On Monday, when we have our review day, I will, before Monday, I will also be sending another document that's got another application with our logarithm equations, and so we'll be covering that on Monday. It's just an application, the way that we can apply our logarithmic equations, okay? So I will be sending that also before Monday. So just a little bit about what's coming up next week. Part of the test on Wednesday, first part on Wednesday, second part on Friday, and you will turn in your homework on those first sections on Wednesday, and then you'll have, and the reason I'm not having you turn it all in is because I want you to have it to review back over before your second part of the test on Friday, okay? It's not that I want you to put off doing your homework, but I want you to have it to review back over when before your Friday part of the test. So I'll spell all of this out to you and the facilitators. Facilitators, you'll be crucial in getting, you always are crucial in all of that happens here, but especially with a two-part test, okay? And I will give you an email also on that information. So students, do you have any questions that you can think of right now? Okay, if we don't have any questions, then we're going to move on in our solving of equations. Let me just back up a little bit and review just a tad. Okay, on our exponential equations that we had started on Wednesday, okay, the first type, I call it type 1, that we covered on Wednesday, was where we can make the bases the same. So, and I won't give anything, let me word it this way. If you can't make the bases the same, it's going to be obvious, okay? Be sure that you are familiar, and you should be, with your powers of 2, your powers of 3, 5. Those are the basic ones that we would be dealing with here, okay? And remember, get the same base. Then you can just remove those bases and set your exponents equal to each other, and then solve for x. Now, any value in an exponential equation will be acceptable. An exponent has no limits, okay? There's nothing that it cannot be. In other words, the domain, it can be any number an exponent can. Now, we're going to find different when we get into our logarithmic equation. So I make that statement because we will have to check with our logarithmic equations. But any number, any solution that you get with your exponential equations is an acceptable value. Okay, any questions there? Okay. As we move on to the next page then, now, let me also point out that here, the directions tell you what to do. On the test, the directions won't tell you what to do. You're going to have these types of equations, 2 types in your exponential and 2 types in your logarithmic equations, and you have to know how to do it without me giving you instructions. Just, I will say, solve, okay? Now, this type here, I call type 2, and this is when we cannot get the bases the same, or make the bases the same. Let's use the word make. Didn't mean to scribble there. When we cannot make the bases the same. Now, when we cannot, then we use log if we're in base 10, or ln. And we're going to log or ln both sides of the equation. Make yourself a note too that we would need to isolate the exponential expression. Remember, back in a previous unit we had to do a lot of isolating. We isolated our radical part or isolated our rational exponent part. Here we will isolate the exponential expression. Okay, so when we cannot make the bases the same, we're going to use log if the base of the exponential part is the base 10, or ln if it's anything else. Both sides of the equation we're going to log or ln. We're going to isolate the exponential expression first. So this actually is the first step. Okay, so this is example 1 here. Okay, we see that. Now, you need to ask in your mind, can I make the bases the same? That's your first question to yourself, because that's type 1. Well, obviously, with a base 10 and an 8 7/100, we can't make the same base. So we say, no, we can't get the bases to be the same. So then the type 2 says we need to make sure that our exponential expression is isolated. So it's on this side, the 10 to the x power is by itself. Okay, we're going to use log or ln depending on my base. Well, since I have base 10, I will use log, and I'll do that on both sides. Log of 10 to the x equals log of 8 7/100. Log on both sides. Then, if you remember your condensing and the properties, the rules that we went through, if we had an exponent here, we can bring it around as a coefficient. So I'm going to move this x around here in front and write it as x log of base 10 equals log of 8.07. Also, another way to think of this, which we covered with the PowerPoint questions basically, is log. Since it's log, it's in base 10, okay? So these are like inverse properties, because log of base 10 of 10, that would mean that is 1, okay? So we end up with just x here equals log of 8 7/100. So basically you have a couple of ways you can think of that. I like to think, because there are some of them that you have to bring this around in front. So if you just be consistent and bring this power around as your coefficient, and then this log base 10 of 10 is 1, so you have x times 1, so you just have x. Now, this log of 8 7/100 is your exact answer. It says give the exact answer. That's the one that goes into my solution set, is the exact. Then it says, and exact answer, and it should say an approximate to 2 decimal places. Actually, I want it to 3 decimal places, everybody. Let's do 3 here. I think the answers that you have in the back of the book are to 3 anyway, or in your answers. So now you go to your calculator and you plug in log of 8 7/100, and you should be getting, and we use the squigglies for approximate, 0.907 when you round it to 3 places. Check yourself on your calculator. Always, when you go to a calculator and plug one of these, that's your approximate. Your calculator gives all of those digits, but it's rounding itself because it can't put any more digits than what your screen will allow. This is the exact, the one that has the word log in it. Any questions there? Okay, the next one. Of course, if you have the base of e and it's isolated, e to the x, again let me back up a minute. We recognize it first as an exponential equation because we've got our variable, the x, in the exponent. Secondly, we ask ourselves, can I make the same base? Well, obviously with an e we can't, okay, with a number over here. So that says I'm in type 2. Then, since I have a base of e, the obvious that I would need to do to both sides would be the inverse, which would be ln. Whoops. So we're going to have ln e to the x equals ln, whoops, that needs to be an 8, 3. Now again, if you want to think of this as the inverse properties, okay, ln and e like we had on that PowerPoint, and they, since they're inverse properties, they're going to cancel each other out, or if you bring that x around to the front, either way you think of it, you're going to end up with just x here, because these are inverse. The ln is base e, so e to what power would give us e, and it's a 1, so this ln of e is 1. So you have x equals the natural log of 83/100. Once again, this is your exact answer, okay? So that goes in our solution set. And then go to your calculator and find the approximate for the natural log of 83/100. Rawls, what did you get?
Negative 0.186.
Say that again.
Negative 0.186.
Okay. And everybody, I like this 0 in front there too. That's kind of standard way to write. Okay. So we've had one with a base of 10, so we used log. We've had one with a base of e, so we used ln. Now let's look at what example 3, unless there's a question. If there's a question, speak up. On example 3, we see again that it's an exponential because my variable is the exponent, or is the power. We look to see if we can make the same base, and of course the base is e, so we're not going to be able to make the same base. So we know we have to log or ln both sides, but we see that my exponential expression is not isolated. I need to isolate this e to the x first. So I'm going to divide both sides by 4 first. So our note here is to isolate e to the x first. Whatever your exponential expression is, you need to isolate that first. So we have e to the x equals, and I have in my notes 2,568 and 2,500. So once again, we want to natural log of each side. Take the natural log of each side. You're thinking, how am I going to undo that e, and the inverse is the natural log, and so that's what we're doing, okay? We're undoing the e base. So again, if I bring that power x to the front, ln of e, of course, is 1. ln of 2,568 and 2,500. So we end up with just x equals the natural log of this. Again, this is my exact. It goes in my solution set. I need to move over here. ln 256825. And then we get an approximate. So Tahoka, what do you get for your approximate value of this natural log?
$7.851.
Okay, thank you. Everyone good with that? Okay. I hope you have some room somewhere on your sheet, because I want to do another example that you're going to need to know, and I can't remember now which problem number it was. I had it marked. Well, I have it marked, but I don't have it. Number 8. Okay? This one is going to be similar. It's going to be a little bit more than what this one is, but I'll see if you can get it figured out. And then if you can't, we'll go over it on Monday. So this is the problem I want us to work now. 6 to the x equals 257. So first of all, we see that it's an exponential equation. Then I'm thinking, oh, powers of 6. Well, powers of 6 would end in an even number, so we know that we can't make it the same base. And we know that even though 6 isn't prime, it wouldn't be like anything else, any prime number to a power even itself. Like 8 is not prime, but it's 2 cubed. 4 is not prime, but it's 2 squared, something like that. So we know we can't make the same base, and that's what I say. When you can't make the same base, it's going to be very obvious to you. So we know we need to take the log or the natural log of both sides. Now, generally we take the natural log. Actually, if you work this one with log, you're going to get the same answer, because when you go to your calculator, you're going to get the same approximation. But I use natural log, so I'm going to take the natural log of both sides. This is where you have to remember, okay, because these don't cancel out. The natural log and 6 don't cancel out. So you have to remember, okay, to bring this x around as a coefficient. X, ln of 6. Now this is times, remember, equals the ln of 257. Now if I'm solving for x and this is times, the ln of 6, just think of it as a number, okay? It's an irrational number, but it's still just a number. So anybody know what we need to do right here, or have a suggestion of, if we've got x times a value, what do we normally do if we're solving for x? And it's multiplication here.
You need to divide.
Exactly. We need to divide both sides by the ln of 6. Divide both sides by the ln of 6. They cancel out on the left side, then we have x equals the ln of 257 divided by the ln of 6. You've got to have the ln, both numerator and denominator. It's not like we did when we condensed into a single log, okay? This is ln in the numerator, ln in the denominator. And we can't divide these two to condense it. This is the exact answer. This is our answer. So that's what goes in our solution set. And then Now when you go to your calculator, whoops, I want the squigglies here. When you go to your calculator, be sure that you close the parentheses after you put your ln of 257 in, and then push your divide button, and then the ln of 6. Be sure you close that parentheses in the numerator. It'll, or my calculator does, it opens it up for me, but I have to close it. So, Idalou, what did you get for an approximate value here?
3.097.
Very good. Okay. So I want the exact in the solution set, and then give me the approximate right there. Okay, so this one will be whatever number I said earlier. Was it 8? Kind of like number 8. You have to do a little bit more on number 8 than this one. But this kind of might help you get started on it, okay? And then if we need to go over number 8 in class on Monday, that'll be great. Okay, so that's our second type of exponential, okay, where we can't make the bases the same. Any questions there? Okay, let's move on then. Oh, I just put my paper. Now we're going to our logarithmic equations, and we have two types of logarithmic equations. One type is where we have logs and a constant. That's the type we'll go over first. Logs and a constant. When we have logs and a constant, we want to have all the logs on one side on one, and then set it equal to your constant. So you're separating logs on one side, constants on the other side. When I say a constant, it's just a number, of course. Any of the others that have log of something, it's going to be on one side. Then just the number by itself will be on the other side. Then we will condense the log side. Condense the side with the logs. So it's going to look like this. It's going to look like log, any base, whatever base is given, of your x's, here's your variable, equals that constant. Log, some base, of your variables, here it'll be here, the domain, equals the constant. When we get it to that form, then we're going to write it as an exponent. Equation. And you're going to say, but we just got through solving the exponent. But now my variable is not in the exponent, okay? It will be of the form b to the constant equals my x. Base raised to this constant power. This is all going back to our what we did originally of changing from exponential form to log form to exponential form. That's what we learned early on. Next we will solve. Then number 5 is crucial, okay? We have to check these. Okay, we have to check because we cannot have the log of something, whatever, to be this cannot be a negative number. In any of my log expressions that I might have in my original equation, my value that I plug in here cannot be a negative number. or it can't even be log of 0. Okay. This, in other words, log, we talked about this, of my domain here must be positive. That was on one of the PowerPoint slides. Okay, so let's go to our next page where we see this type of equation. And we say, okay, now I don't have an exponential, okay, because it's got the word log in there. I see log and I see a constant. So it says we want the log part isolated from the constant, and we want it condensed. Well, it already is condensed. So this one's a very simple one. We've kind of done this type before. We're going to go straight to writing it in exponential form. My base is 5. My constant is my power, okay, raised to the third power, equals x. And of course, 5 to the third power is 125. So my solution is 125. And that's an exact solution. There's not an approximate this time. This is an exact solution. You only have approximates if you have LN there or log. I should have, before I wrote that, 125, if I put it in here in my domain, of course 125 is positive, so it's okay. Now you can think about checking that yourself also. Log base 5 of 125 equals 3. Okay, if we think in our mind how we change these, that's saying that 5 cubed equals 125, going back to your exponential form. And of course it's true. So on this next one, the other type, let me just go ahead and tell you, the other type of log equation has logs all the way across. Instead of log and a constant, it has logs, logs, logs. Only logs, no constant. This one, log and the constant. So we know that we've got to have the log separated from the constant, which is there. My log is condensed to a single log. So now we're ready to go to the exponential form. So, Rawls, give me that exponential form.
Three squared equals x minus 7.
Oops, I didn't hear the first part of that.
3 squared equals x minus 7.
Thank you. 3 squared equals x minus 7. Very good. Okay? Your base, and then your constant out here is your power, okay, equals x minus 7. So 3 squared is 9, equals x minus 7, and we can solve from there. So we would add 7, and we have 16 equals x. Now think about, you've got to check, okay? If I plug this back in for my x, does that make this domain positive? 16 minus 7, of course, is 9, so it is positive. That's what you have to make sure of, that this domain part is positive. So my solution is 16. And of course, when you put that in, I said you would have 9, so you'd have log base 3 of 9 equals 2. When we write that in its exponential form, 3 squared equals 9. And so we know it checks. Okay, questions? We good? Okay, this next one, okay? Notice we've got some log, but we've also got a constant. So we're still on the log and the constant form. The second step says that we want the logs separated from the constant, which they are. Then we need to condense this log side. Okay? So, Tahoka, with a plus sign in here, how am I going to condense this log side?
By multiplying.
Very good, okay? Log base 6 of x plus 5 times x. The sum, we condense it by multiplying, equals my 2. Okay? So now we're ready to write that in its exponential form. Idalou, what would be the exponential form?
6 squared equals parentheses x plus 5x.
Okay? X plus 5 times x. So now then, we want to actually multiply this right side out, and we can go ahead and square the 6. So that's 36 equals x squared plus 5x. And we recognize this to be a quadratic equation. Quadratic equations, we need to set equal to 0. So this is something that we learned early on, okay, or that you already knew coming in, but we refreshed it anyway. So we're going to set this equal to 0. I want my x squared positive, so I have x squared plus 5x and then a minus 36. And we need to factor. Yay! Who's going to get that factored for me?
X plus 9, x minus 4.
Okay, x plus 9, x minus 4. You can go through your factors of 36. 1 and 36, 2 and 18, 3 and 12, 4 and 9, 6 and 6. A difference of 5. So, of course, it's the 9 and 4, and we want the positive 9. So, x plus 9 equals 0. X minus 4 equals 0. X would equal a negative 9. X would equal 4. Everybody, crucial. You must check. Put this back in the domain. Okay, negative 9 plus 5 would give us a negative 4. I cannot have a negative domain. And if put the negative 9 there, of course it would be negative. So that is not a solution. Negative 9 is an extraneous solution. Putting in my 4, 4 plus 5 would give me 9, which is positive, and 4 here is positive. So 4 is my solution. And of course, any of these, you can plug them back in and check, okay? Any equation, you can plug that back in and check it. Okay, any questions? Or as we turn the page? Okay, moving on. Example 4. Okay, I look at it and I see log, but I see a constant. Okay, so that tells me again it's the log in constant form, not logs all the way across, log with a constant. So we're going to, they're separated, they're logs on one side, constant on the other side. That's already done for us. So we need to condense this. Tohoku, condense that for me.
Log base 4 of x plus 2 divided by x minus 1.
Very good. Okay, the minus sign, remember, means it's going to be a quotient then when you condense it. Equals the 1. Okay. Rawls, give me the exponential form.
4 to the first power equals x plus 2 divided by x minus 1.
Okay, plus 2 divided by x minus 1. Very good. Now we know 4 to the first power is just 4, so I'm not going to take an extra step there. But now we need to get rid of this denominator of x minus 1. Remember how, somebody tell me what I need to do for my next step.
Multiply both sides by x minus 1.
Very good. Multiply both sides by x minus 1. Okay, that cancels it out of the denominator there. So we have 4 times our x minus 1 equals an x plus 2. And then I'll distribute here. 4x minus 4 equals x plus 2. Notice we don't have a squared, so we're just solving a linear. We're just going to get our x's on one side and our constants on the other. So minus x. So we'd have 3x minus 4 equals 2. And a plus 4. 3x would equal 6. Divide by 3. So we get x equals 2. Now, be sure that you plug that into your domain and check. Okay? X plus 2. 2 plus 2, that would be positive. 2 minus 1, that would be positive. So both of these domains are okay with my value of 2, or okay meaning they're both positive. So my solution is 2. Okay, now we look at example 5. We see logs all the way across. Okay, log, 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 no constant. Okay, in other words, no number like by itself without a log. Okay, with attached to it some way. So this is the second type where we have all logs all the way across. Okay, what we do here is we condense both sides if necessary. Sometimes it's just one side, but make sure that both sides are condensed. And after we've done that, we can drop the logs. Used to books, and I don't know if they still do it so much anymore, we'd say take the anti-log. Okay. Very similar to when we had the same bases in our exponential, we could drop those bases and just set our exponents equal to each other. Basically, we're dropping the log on both sides and just setting those domains equal to each other. Okay, so we see on this one, the left side has a single log, so we're good there. We don't have to do anything there. The right side has two different log expressions, log x plus 3 and plus log of 3. So it's a plus, so I need to change that to a product, log of x plus 3 times 3. So now I've got it condensed down to just a single log on both sides. So I can drop the log or take the anti-log. And I just am writing the domains equal to each other. 2x minus 1 equals x plus 3 times 3. We will distribute over here on the right side. 2x minus 1 staying on the left side. So we would have 3x plus 9. Be careful when you distribute. And again, we just have an x to the first power. We don't have any squared, so we're just solving a linear. So a minus 2x, solve for x. And a minus 9. So I'm getting x equals a negative 10. It doesn't matter, well, in this one it does, okay? But you can't just look at the value of x, okay? You have to plug that value of x back into the domain. So I plug it in here, a negative 10 times 2 would be a negative 20 minus 1, so that makes it a negative. So this one does not work, but you're checking it into the domain. You're not just looking at this value of x that we got. So if negative 10 does not work, and that's the only value I got, then what is our solution, anybody? How about no solution? No solution. Okay? There is no solution. The only one I got doesn't work, so it's no solution. Any questions on that one? Okay? Let's look at the next page. Example 6. Okay, we see logs, so we know it's not an exponential. We have two types, log with a constant or all logs, and we look at it and we've got log here, log here, log here, and no term that's just a single constant. So this is another all logs. So we know we need to have each side condensed to a single log. So we have log base 6. This side's already a single log. 5x plus 1. I condense this side because I've got two logs here. I need that condensed to a single log. I'll write log base 6 and you tell me what to put there. Idalou?
2x plus 3.
Log base 6, 2x plus 3 times 2.
Very good. You've got the plus there, then you're gonna write it as a single log as a product. 2x plus 3, and then times 2. We've got our single log on each side. We can drop the log or take the anti-log, whichever way you want to think of it, so that we're setting our domains equal to each other. 5x plus 1 equals 2x plus 3, and then times 2. I started right at 3, but it's a 2. Distribute over here on this right side. 5x plus 1 is good for us. Distributing would be a 4x plus 6. Solving for x then, well again, no squared, so we can just solve for the x minus the 4x. So we have x plus 1 equals 6. Minus the 1 would give us x equals 5. Now, just because that is positive doesn't necessarily mean that it will make each of our domains positive. You must check it back in your domain, each one of them. Okay, that would be a 5 times 5, 25 plus 1, that is. And of course this one is. So it works, but it's not just because this is positive. You check it into your domain. Any questions? Our time is like. Yeah, I think we have time. Let me just show you how you can actually plug this in and check. Log base 6. Okay, I plugged that in and I said 26 equals log base 6. When I plug the 5 in here, I have 13 plus log base 6 of 2. Now you do have to do a little bit of work here to realize that you're going to have to take this sum of the two logs and do the product. Log base 6 of 26 equals log base 6 of 13 times 2. And 13 times 2 is 26. So log base 6 of 26 equals log base 6 of 26. Multiplying those two together. You're applying your log properties, your log rules. Okay, example 7. Okay, we don't see any exponents. We see logs written, so we know it's a log equation. Okay, we know we've got two types of log equations, either log and a constant or logs all the way across, and I'm looking log, 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 but here's a constant. Okay, so that tells me that it's the first type where I want all of my logs on one side and my constant on the other side. I'm going to condense that log side. Okay, so let's go to Tahoka. Tahoka, condense this log side for me. We've got a plus and a minus.
Log base 2 of x minus 6 times x minus 4 divided by 6.
Divided by what?
I mean x.
Okay. Equals the 2. Okay, very good. Now, Rolf, what was our next step? We've kind of gone away from these. What was our next step when we had the log and the constant?
Oh.
We get it in our exponential form.
Okay, we write it in our exponential form, which would be, go ahead and tell me.
2 squared.
2 squared equals x squared minus 10x plus 24 over x.
Okay.
Oh, I factored it out.
Right. They've already multiplied this. I'm going to write this step so that we don't get anybody confused. We're taking too much. So my exponential form will be my base raised to the constant and then my domain here. Then go ahead and multiply, or you can multiply. I'm not saying that that was wrong, but I just wanted to show that step. Here we would have 4 equals, and I think they said x squared minus 10x plus 24, and then divided by x. Idly, what do I need to do next?
Multiply the x on both sides.
Okay, multiplied by the x, because I've got to get rid of that x in the denominator. Okay, so this side would be 4x, and then I would have x squared minus 10x plus 24, This time I do have the x squared, the quadratic, so I need to set it equal to 0. 0 equals x squared. This will come across as a minus 4x, so that'll make it a minus 14x plus 24. The factor race is on.
X minus 12, x minus 2.
Good. X minus 12, x minus 2. Again, you can write those factors of 24 to help you if you need to. Okay, I'm going to move right up here, everybody. X minus 12 equals 0. X minus 2 equals 0. I'm getting x equals 12 and x equals 2. Now this is a perfect example. Both of these are positive, but that doesn't necessarily mean that they're both solutions. We have to check it over here in our domain. 12 minus 6, yeah, that would be positive. 12 minus 4, that would be positive. And of course just the plain old 12, that would. So 12 is a good. Let's check the 2. 2 minus 6 will give me a negative 4. It doesn't matter what happens in the rest of those. If one of them is negative, then it's excluded. So my only solution is 12. Or actually I should say it's extraneous, but we don't write it in our solution set. Any questions? Okay, I think we may have just a minute or so left. Be sure that you're doing your homework. There's this next page is the lab. Okay, I will be posting this and I will be getting the video up today so that on Monday, our review day, I've got a little bit more, like another few examples that I want to make sure, and so we can cover everything. Any questions, okay? We'll see y'all on Monday. Have a good weekend.